All matter is made of atoms. The nucleus, containing protons and neutrons, holds immense energy. Nuclear power plants harness this energy through nuclear fission. Certain isotopes, like uranium-235, are unstable. They readily undergo fission when struck by a neutron, releasing more neutrons and vast amounts of heat. Released neutrons trigger further fission events, creating a self-sustaining chain reaction. This reaction is carefully controlled in a nuclear reactor. The reactor core is the heart of the plant. It houses the fuel rods containing enriched uranium and the control rods that regulate the chain reaction. Fuel rods contain pellets of enriched uranium dioxide. The arrangement maximizes neutron interactions, ensuring efficient fission. Control rods made of neutron absorbing materials like boron or cadmium can be inserted or withdrawn to slow down or stop the fission reaction. A moderator, often water or graphite, slows down neutrons, increasing the probability of them being captured by uranium nuclei and causing fission. The immense heat generated by fission is removed by a coolant, usually water, which circulates through the reactor core. In a WR, the primary coolant loop is kept under high pressure to prevent boiling. This heated water then heats a secondary loop to create steam. In a BWR, the water in the reactor core is allowed to boil directly, producing steam that drives the turbines. This is a more direct but potentially less stable approach. Regardless of reactor type, the heat generated produces high-pressure steam. This steam is the working fluid that drives the turbines. The high-pressure steam spins massive turbines, converting thermal energy into mechanical energy. These turbines are connected to generators. The rotating turbines drive generators, which use electromagnetic induction to convert mechanical energy into electrical energy. After exiting the turbine, the steam is condensed back into water. In a condenser, this requires a cooling system, often a cooling tower, to dissipate the heat. The condensed water is pumped back into the reactor to repeat the cycle, creating a continuous loop of energy conversion. A massive containment structure surrounds the reactor to prevent the release of radioactive materials in case of an accident. Nuclear fission produces radioactive waste, which requires careful handling and storage due to its long half-life. Spent fuel is initially stored in cooling pools to dissipate heat before being moved to dry cask storage for longer-term management. Reprocessing can extract usable uranium and plutonium from spent fuel, reducing the volume of waste and potentially generating more energy. The most widely accepted long-term solution is deep geological storage in stable rock formations to isolate the waste for thousands of years. Nuclear plants have multiple layers of safety systems, including automatic shutdown mechanisms and emergency core cooling systems to prevent accidents. Redundancy and diversity are key principles in nuclear safety. Multiple backup systems are used to ensure reliable operation even in case of component failure. Nuclear power plants are subject to stringent regulations and oversight by national and international organizations to ensure safety and security. Probabilistic risk assessment (PRA) is used to identify and quantify potential accident scenarios and their consequences. Advanced reactor designs, such as small modular reactors, SMR, and generation for reactors, offer improved safety, efficiency, and waste management. MESA's smaller factory-built reactors that can be deployed more flexibly and offer enhanced safety features. Generation 4 reactors aim to be more sustainable, safe, and proliferation resistant. They explore different coolants and fuel cycles. Nuclear fusion. The process that powers the sun offers the potential for a virtually limitless and clean energy source, but remains a technological challenge. Tokamaks and stellarators are two primary approaches to confining plasma. In fusion reactors, using strong magnetic fields. Nuclear power, both fission and potentially fusion, can play a significant role in meeting global energy demands while reducing carbon emissions.